Bridges are integral elements of transportation infrastructure that allow humans and vehicles to cross otherwise inaccessible terrain, such as rivers and roads. Behind every bridge is precise engineering, such as structural analysis and design consideration. To prioritize stability for our engineering team, the assignment was to design and build a spaghetti bridge that could carry as much weight as possible under some dimension and material constraints. The realistic exercise enabled us to transfer theoretical knowledge into practical application in an actual but imaginary environment. The challenge required us to use only dry spaghetti and glue to construct a functioning bridge, simulating real-world design conditions on a much smaller scale. After researching various bridge types, including beam, truss, cantilever, arc and suspension, and cable stayed, we collectively chose to construct a truss bridge. Truss bridges use triangular units to distribute loads efficiently through compression and tension, making them one of the most reliable and structural sound bridge types. We also made our design more specific by incorporating a triangular sloped roof, taking inspiration from arc and cable-stayed bridges to provide more strength and less bending stress. Throughout the project, we collaborated on every stage of the process, researching, designing, constructing, and troubleshooting. There were various setbacks we faced, including a surprise collapse of one wall of a bridge just hours before testing, which required emergency repair. Nevertheless, we were successful in finishing the bridge and gaining valuable lessons regarding structural behavior, limits of materials, and safe construction techniques. The following report documents our design choices, construction, teaching results, and lessons learned regarding on how we can improve future construction. A bridge is horizontally structures that span between two different locations. The sole purpose of a bridge is to carry any bare vertical loads that could be anything from live loads to dead loads, and loads like people and vehicles. Bridges are built over various obstacles such as over water and over land. Bridges can be built over water to facilitate travel and crossing over rivers, lakes, and even parts of the ocean. Bridges built over land are most common as they are made over things such as roads, railways, sometimes even natural landmarks such as valleys and canyons. Simply, bridges can be built for transportation purposes, but can also be designed for aesthetic or recreational purposes, such as attracting tourists or enhancing landscapes. There are various different types of bridges. Beam bridges are the most known and oldest bridge form. It carries vertical loads by bending. It goes through horizontal compression on the top of the bridge, while the bottom goes through horizontal tension. Truss bridges. This type of bridge is recognized for its unique design composed of wooden, metal, triangle-shaped trusses. Since triangles can't be affected by stress compared to other shapes, it makes truss bridges very stable. The reason for this is that the triangle's rigid shape is fixed by its three sides, therefore being the strongest shape for the structural integrity. They distribute stress equally throughout compression and tension. Suspension bridge. A type of bridge that is supported by large cables built above it, usually anchored at both ends and draped over tall towers. This design is usually used for longer bridges as it's ideal for crossing over water and valleys. It is known by its aesthetic appearance as well as the ability to cover great distance than other bridge types. In contrast, they are the most expensive bridges to build due to their complex components and construction methods. In modern day, these bridges are primarily built for vehicles. Cable-stayed bridges. A cable-stayed bridge is distinguished by its deck being upheld through many diagonal cables. Each cable is anchored directly to one or more vertical towers, which are called pylons. The cables attached to the pylons are set in patterns like fans, harps, and remain stretched and directly support the deck's weight, which therefore transfers the force to the tower. The tower then channels the load into the bridge's foundation, working under compression. The stretch itself is crucial, as it subjects the deck to horizontal compression, making it so that the bridge is a great choice for medium to long spans. Cantilever bridges. A cantilever bridge consists of three sections: the two outer spans, which extend from opposite banks, and then a central span that rests on top of the arms. The outer span is over the gaps, such as rivers, valleys, etc., reaching towards each other, while the central section bridge is the rest of the distance by resting on the free ends of the projecting arms. Lastly, there's the arc bridge, which relies on its curved arc structure as the main support. This type of bridge relies solely on compression, as it transfers the load into compression that pushes out towards the end, where the strong abutments hold everything together. The arc bridge design allows the bridge to be constructed with different lengths spans with less material compared to the other bridge types. After thorough discussion on what type of bridge to choose for our spaghetti bridge, we went ahead and chose the truss bridge. Our group first had the idea of going with a beam bridge with a flat roof on top. This bridge was initially planned to have two truss sides of 500 millimeters, a flat rooftop, and fixed ends on each side, as seen in Figure 14. After some more research, we came to a stop, and we discovered that a truss bridge holds more weight than a beam bridge. So we then scrapped the idea and went ahead by constructing a standard truss-only bridge. To make the bridge unique and have the capability to carry more weight, we decided to build a bridge which had a triangular roof that slopes upwards. The main reason for this was that a triangular evenly distributes the load through its sides and down the support, therefore making the bridge stronger and more stable when compared to a flat beam bridge. The second reason is that triangles are also used in real bridges and most roof structures, as their shape prevents bending that allows them to stay fixed and rigid, thus supporting more load without deformation or collapsing. Constructing our spaghetti truss bridge was a team-based process that included planning, testing, construction, and troubleshooting. We had some members with special tasks, but we as a group made most of the decisions to ensure the same uniformity and precision remains throughout the project. We had a number of meetings prior to even commencing any construction on the bridge so that we can finalize how the bridge would be designed. We learned about various types of bridges and their strengths and weaknesses, and decided to use a truss bridge with a triangular sloping roof. This was because the truss bridge was able to evenly spread loads, and the triangles contained inherent structural ability. We then made the final measurements of our bridge based on the competition and the project requirements. We wanted the bridge to measure 500 millimeters long with a symmetrical truss sides and a strengthened deck. In preparation, we used uncooked spaghetti as the main building material and superglue at each joint and connection. Spaghetti strands were cut and measured into accurate lengths based on the truss design. We labeled and grouped each standard category so that we would remain organized and uncluttered during assembly. We began by building the two major truss sides. We bonded strands of spaghetti together to form triangular units with a printed cardboard template. Each triangle was carefully aligned to ensure similarity and stability. We let the glue cool and harden first before moving the truss to prevent deforming them. Once we had completed the truss walls, we built the bridge deck, the lower level connecting both sides. A number of strands of spaghetti were glued together to create thicker, more durable beams for the deck. Cross bracing below the deck was installed using diagonal pieces to prevent twisting and sagging when loaded. We installed a triangular-shaped roof to improve overall stability and load-carrying capacity. The roof functioned as an upper truss, reducing lateral movement and overall stiffness. We linked the top of the two truss sides with diagonal horizontal members. The roof shape mimicked structural design features in real bridges and buildings, where the triangular structures are used for their rigid platform. We then glued the roof, deck, and truss walls together with precision, making sure that all components were vertically and horizontally aligned. Weak points were also reinforced and given extra bracing, specifically around fixed supports and joint. We inspected the bridge on all four sides, looking for misaligned joints, weak glue bond points, or structural imbalance. Worrying areas were re-glued or given extra spaghetti members to support them. We let the final shape rest and set for a few hours before testing the ultimate strength. Approximately 3 hours before our actual testing, our team encountered a tremendous blow. One of the truss walls of the bridge collapsed. The collapse happened when we were moving the bridge from the drawing section to testing section. It resulted from weakened glue joints and no reinforcements among some of the diagonal and vertical members. The collapse did have a visible impact on our test and overall result, as a part of our bridge had to be rushed in repair before testing. The structure was less stable and robust as it would have been in the normal state. The rapid repair meant that some of her joints were not aligned correctly and nor dried before loading. We believe that premature failure and emergency regluing weakened the overall strength of the bridge. As a result, it likely failed at a reduced load than it would have not been able to have it not initially failed. There was so little time left before testing that hasty solutions were a bigger problem than measured. Deliberate strengthening. The added pressure amplified the likelihood of mistakes in the final steps. A first lesson learned was that glue cures and hardens slowly. Tactile handling or applying stress to the bridge too soon weakened structural integrity. We realized that the joints of the glue are the weakest points in the structure. Even if the members of spaghetti are robust, poor joints will result in overall failure. Having spare prefabricated components or backup plans would be time and panic saving if major components fails close to testing. For subsequent constructions, we would apply more than a single layer of glue to every joint and perhaps even sandwich the spaghetti members for added strength. We would complete construction at least 24 hours before testing, allowing the entire structure sufficient time to dry thoroughly and leave it undisturbed to prevent pre-test stress. After the bridge is built, it should be kept on a horizontal plane and shifted only once to test it. Raising or shifting beforehand puts extra stress. If time permits, a small trial load test may be conducted one day in advance to locate weak points prior to actual testing. Through every stage of building, communication was central. Every group member alternated working on various sections of the bridge. We switched roles to ensure everyone had a hand in and remained interested. When issues arose, such as spaghetti strands cracking or glue hardening too quickly, we collaborated to resolve quickly. The Spaghetti Bridge project gave us the chance to learn the fundamentals of structural engineering in the field in an interactive fashion. Overall, the project was valuable in teaching us critical skills in engineering, design, problem solving, and collaboration. It proved that even simple materials such as spaghetti can be used to teach sophisticated principles when paired with careful design and cooperation. The experience reinforced the notion that engineering is not necessarily about constructing things. It is about learning how and why things succeed or fail, and continually learning from doing so.